Hi, chemistry students. Today we're going to take a look at acid-base concentration, and we're going to be looking at tools that we use to find the concentration of acids and bases. So we first should talk about a titration, and that's the main idea we're looking at today as far as a process that we use in order to figure out these unknown concentrations. And a titration is a very deliberate neutralization process that's used to find an unknown concentration. So to perform a titration, a standard solution is required. And what a standard solution is it's a strong acid or strong base, and it has a known concentration. In other words, so you know the concentration of that acid or that base. And to find the concentration of the opposite, so in other words, if you know the concentration of a strong acid and you want to find the concentration of a strong base, we would use a titration and we would neutralize the acid and the base. And drop by drop, you do it until you see when the solution is neutralized. Okay? So, and that's what it touches on here. The standard solution is usually added to a sample of unknown concentration until neutralization has occurred. And right here, we have a diagram of the sort of apparatus that we would use. And so just to kind of get a feel for what we have here, so this would be our unknown solution. Like we would know the solution, we just wouldn't know the concentration of it. And the known concentration of either the acid or the base would be in here. And drop by drop, you'd add it to the flask and you'd have an indicator of some kind in the solution to let you know the moment that the solution is neutral. And actually, you'll be able to figure that out very quickly with the use of an indicator. And the apparatus has a special name, and that special name is a Barré, and it's used to control the additions of acids and bases in the titration. And the Barré readings are used to determine the volumes of acids and bases in the titration. And actually, I don't think it's said Barré, I think it's Barrette. We're not able to watch the demonstration, so we'll just move on. When an acid and base are neutralized, the exact point of neutralization, the number of moles of acid is equal to the number of moles of the base. Okay, that's very key. The point at which the amount of standard acid or base solution added neutralizes the unknown sample is called the equivalence point. The equivalence point can be determined by adding a pH indicator to the unknown sample or by using a pH meter to measure the pH change as standard solution is added to the sample. If indicator is used, the point in the titration at which the desired color forms is called the endpoint of the titration. The indicator is chosen so that the endpoint and the equivalence point are very close. The endpoint and the equivalence point are not the same thing. Okay? Okay, so When performing an acid-base titration, both the standard and unknown solutions are placed at separate burettes. For this example, we're going to determine the concentration of hydrochloric acid solution using a 0.1 molar solution of sodium hydroxide. So step by step, here's the steps that we would take. Step 1. Fill each burette and take the initial volume readings from the bottom of the meniscus. And all that basically means is, of course, if this is your test tube and you have something like that, then the readings you would take would be right from that bottom of the meniscus right there. Okay. Step 2, release a sample of the unknown acid solution into an Erlenmeyer flask. Read the acid volume in the beret, and that would be the final acid volume. Okay. Step 3, add an indicator like phenolphthalein. The endpoint will be reached when the sample turns a light pink, and phenolphthalein turns pink at a pH of about 8.2. So slightly basic. Step 4, slowly add the standard base solutions to the flask while stirring or swirling until the solution in the flask turns a light pink and stays pink in the case of phenolphthalein. Take the reading on the base burette and call this the final base volume. Step 5. Repeat this procedure until there are several trials reflecting consistent data. The data will be used to determine the unknown concentration of the acid. So that's the key thing here. This isn't a one-step process. You're going to be doing this maybe 3-4 times, and then you'll average your result, and that way your data is going to be the most accurate. Now, let's use titrations to determine an unknown concentration. So, let's look at the math behind this. Once you've determined the volume of an unknown acid required to neutralize a volume of a base with a known concentration, then we can find the concentration of the acid. So, here's some sample data that might be the case. So, the final burette reading of the base was 14.45 mils. The initial reading was 0.62 mils. For the acid, there's the 2 right there. So now, how do we use that to find the concentration? We need to find the volume of the acid and base used. So we just subtract final minus initial, and that gives us the volume of the acid and the volume of the base. And then we make sure to turn both of those into liters by dividing them by 1,000. Then we need to find the moles of the unknown solution. So the neutralization equation, we need to go ahead and write out the neutralization equation. And the important thing that we see when we do that is that there is a 1-to-1 molar ratio with hydrochloric acid and sodium hydroxide. So we know that there is 0.001383 moles of sodium hydroxide used, and we find that by multiplying the molarity, or the concentration, by the liters, or the volume of sodium hydroxide used. So that's important, because if that's the number of moles of sodium hydroxide, we know that also, because of that 1-to-1 molar ratio, we know that that will be the number of moles of acid as well. And we also know that the volume of the acid used was 0.01144 liters. So if you divide those together, you get a molarity or concentration of 0.121 moles per liter. So that is the concentration of the unknown acid. It's 0.121 moles per liter. Okay. So you have to write out the balanced chemical equation using the molar ratios between the acids and the bases. Find the number of moles of the unknown substance and divide by the volume of it that you needed, and that will help give you the concentration. We're going to look at one more thing here today. We're going to look at titration curves. A titration reaction can be graphed. The data plotted would be a volume of acid or base versus the changes in pH. In this example, 25 mils of a hydrochloric acid solution is titrated with a 0.1 molar solution of sodium hydroxide, and we have the balanced chemical equation. At the equivalence point, the hydronium ion and hydroxide ion concentrations are equivalent, as are the sodium and chloride ion concentrations. The solution is neutral. That means that the pH is 7. If we graph the change in pH as the base is added, the expected titration curve will look like this. It's not a linear curve. You see it's a gradual curve. You see it's a gradual curve here. I'm just going to get my pointer. Gradual, 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 and then it shoots way up, and then it just kind of levels off. So the equivalence point is found in the center of the steepest portion of the curve. The steepest portion of the curve, okay? So the steepest part of this curve is, of course, this part of the curve. So the very middle of that, that's the equivalence point, okay? The equivalence volume is 25 mils, and that is found right here on the graph, and it's 25 mils. It's 25 mils of 0.1 molar sodium hydroxide, and because there's a 1-to-1 molar ratio with sodium hydroxide and hydrochloric acid, if we find the number of moles of sodium hydroxide, they'll also equal the number of moles of hydrochloric acid. So we find that there's 0.0025 moles of sodium hydroxide, and we find that by multiplying the concentration by the volume. So to find the concentration of hydrochloric acid, we know what the number of moles is, and we also know the volume from that graph. So if we divide them, we get a 0.1 molar solution of hydrochloric acid. The pink on the graph indicates the color change of phenolphthalein with the pH change. Despite the color change at a pH higher than equivalence, the difference is not significant because the curve is so steep at the equivalence point. So the pH changes drastically at the equivalence point. So that also helps us because even though the graph turns pink at a pH of about 8.2, or the solution turns pink, well, the graph turns pink as well, But the solution terms pink at a pH of about 8.2. Because it's so steep, it's not going to be a big difference between your equivalence point. Okay? All right. So there'll be some practice questions on this. Please try some. And if you need any help, please ask.